Okay, the last time we saw, the last thing we saw the other day was just an estimate of the ignition time, okay, for the Semenov system, so a constant volume, so-called batch reactor, okay, and just to illustrate to you the various mathematical techniques that we can use, okay. And in this case, we had done something very similar to a perturbation analysis, where in the limit of very high activation energy. And basically what the result of this was is this thing here. And what you can see is that the higher...
Professore, non ci sono problemi io, ma non sta condividendo lo schermo forse.
Ah, ok, scusate. No, non sto condividendo perché non sto condividendo, giustamente. Ok. Grazie, ditemele subito queste cose, se no io vado avanti 10 minuti. Lo vedete adesso?
Sì, sì.
Okay. I was talking about the ignition time, okay, the last thing we saw the other day. And very simply, we found out essentially that the ignition time is inversely proportional to the heat of reaction, which makes sense. It is also inversely proportional to the initial concentration of the reactant. Now, you can't really relate the ignition time to the activation energy, which is stored in this beta here, simply because we had made the assumption that beta 0 is much larger than 1. So what I mean by this is that once you make an assumption at the beginning of your theory, okay, you have to stick to that assumption, okay? And so because we assume that beta is very large, now you can't change beta like you want, okay? You can't, for example, say that beta is low or it's increasing or decreasing. No, beta is only very, very large, okay? That's the assumption we made. So what you can say is, in fact, that the only thing you can say here is that the ignition time really is inversely proportional also to this group of terms, which is a reaction rate. So generally speaking, okay, the larger the reaction rate, the smaller the ignition time, okay? But again, I think it's a very elegant way of... Can you hear this terrible noise? There is some construction going on. Ci sta un po' di casino fuori, lo sentite?
Poco in sottofondo.
No.
Ok, perché per me è assordante, diciamo. Aspettate che faccio un clear canvas, così iniziamo da zero. Allora, vediamo. Let's try and finish the Semenov system, okay? There are a few things that are left for the Semenov system. One thing is a very old, very sort of historical assumption that or approximation, which is called the Frank-Kamenetsky with a double I approximation. Okay, we're going to be using this approximation in the analysis of the Semenov system, okay? It is straightforward, so I'll try to skip a few steps if I can, so as to not make it too boring. Suppose that the reaction is zero order, no? So n equals 0, that's the order of the reaction. That means essentially that the reaction rate is equal to, well, a reaction constant, which is an exponential function of the temperature, times a concentration, right? A molar concentration to the power of n, okay? In this case, N is 0. So it simply means that the reaction rate is not dependent on the concentration. So it's the simplest possible reaction rate expression, right? So it's only KT, okay, which has the form, for example, an even simpler form is when you have the pre-exponential factor as just a constant A times E, okay, to the minus E over RT, okay? It's a very, very simple, simplest possible Arrhenius form, okay? Now, what do we know? We know that the activation energy is very high, right? So essentially, this number here can be assumed to be, let's say, order 10, but in any case, much larger than 1, okay? So the Zeldovich number is high, okay? That's one thing that we can say. And so in the Frank-Kamenetsky approximation, what one does is, well, if we have a large number, maybe we can do some sort of approximation. So one of the things that you can do, for example, is in the neighborhood of the temperature equals to, say, a fixed temperature, we'll call it T1. What we can do is we can take this this expression, okay, and we can expand the 1 over T in a Taylor series, okay, near T1. So we would have something like this: 1 over T1. And then the derivative, okay, so it's 1 over T1 squared, okay, T minus T1, okay, and then, you know, on and on with higher order terms, so quadratic, cubic terms, etc. So what we're just doing is simply take any temperature, T1, okay, and we expand this, this 1 over T in a Taylor series, okay? Why do we do this? Well, because essentially we want a simpler form of the reaction rate, okay? The reaction rate is, of course, A e to the minus E over RT. So suppose we retain only the first two terms here, okay? So this would be approximately equal to the first term, which is AE to the minus E over RT1, which is a constant. This whole thing is a constant. We can call it, I don't know, A prime. And then the only dependence on temperature is retained in this form here. So we will have E to the minus E over RT1 squared T minus T1. Okay? So if we call A prime this factor here, we can also call, for example, theta, this quantity here, E over RT1 squared, okay? Then essentially the Frank-Kamenetsky expression of the reaction rate becomes omega equals A prime, we can call it omega prime. So omega is approximately omega prime equals A prime E to the theta T minus T1, which is a little bit more benign. Okay, and this is only valid in the vicinity of T equals T1, okay? So we can prove a couple of things, okay, that in T1 we can say that you can prove it very easily that the actual real expression of the reaction rate coincides with the Frank-Kamenetsky expression in T1. So the two expressions are the same. There's no error. There's no error introduced in T1. Not only that, but you can also prove that the derivative, okay, with respect to temperature calculated in T1, okay, of the actual expression omega is equal to the derivative of the Frank-Kamenetsky form of the reaction rate in T1. So what do we mean by that? Graphically, well, we know it's an exponential dependence, something like this, okay? So if this is the original form omega, and this is T1, okay? We have that the omega prime, the Frank-Kamenetsky, is essentially something like this. So they touch in T1, they're the same in T1, and they're parallel. They have the same slope, okay? They have the same tangent. Okay, sometimes it's useful to have this expression. Bear in mind that it's an expression which is only valid around T1, okay? As you can see, as we move away from T1, the error can be very big, okay? In fact, you can also prove, I'm not doing this, okay? So it's just a waste of time to do it, but you can prove that the actual error, okay, introduced, so we define it simply as the difference, okay, it's a quadratic error, so essentially it's something like this. T minus T1 squared, okay? So that's the error that you make in considering the reaction rate equal to the Frank-Kamenetsky approximation. Now, what does that mean? Well, obviously, as we move away from T1, okay, this quadratic term will kick in. But remember that theta, okay, is equal to essentially e to the RT1 squared. So we can call it e to the RT1, okay, divided by T1, which is of the order of, let's say, 10 divided by T1, okay, which is in itself a small number, okay? So this coefficient here is small. So it's essentially an acceptable, let's say, form or assumption, which is a little easier to handle, okay? And it's valid in the vicinity of T1 with small errors. Of course, if you move away from T1, okay, the assumption completely breaks down, okay? And it's not a valid assumption anymore. It's not a valid expression. You can hear me, right?
Sí.
So let's go back to the Semenov system, okay, and see if we have any sort of utility in the Frank-Kamenetsky approximation. Let's say that I'll anticipate some results. We will recover some of the things we already know. And also it will give us some sort of guidelines on how to non-dimensionalize the system, and then that will be useful for later on. But what I'd like to really stress is that if we substitute, okay, I'm going to repeat it later on, if we substitute the Frank-Kamenetsky form of the reaction rate in the Semenov system, which is a set of two ordinary differential equations, so it's the time-evolving system, okay, we cannot integrate the system. okay? Because if we integrate the system, the temperature is going to increase, okay? And it's going to move far away from the temperature T1 or whatever we choose, okay? Around which the Frank-Kamenetsky assumption holds. So we're moving away from the neighborhood where the Frank-Kamenetsky assumption holds, and so it breaks down. Okay, so we cannot integrate it, but we can do a series of things. So let's let's write down the Semenov system. If you remember, it had this form here. So we have an equation, an ordinate differential equation for the temperature is equal to Q plus, which is the heat generated by the exothermic reaction, okay, and a heat loss Q minus term, right? T minus T0, and obviously the rate of change of molar concentration is the usual minus C K0. This could be K or K0, it doesn't really matter, minus E over RT. Okay, so let's start from the Semenov system that we know. Okay, and I may be asking, okay, what happens if I use the Frank? Let's abbreviate it to Frank-Kamenetsky. Okay, approximation. What happens? Okay. Well, let's use it in the vicinity of T0, okay, which is the wall temperature, okay? It could even be assumed as the initial temperature of the gas, but I mean, you know that T0 is the temperature of the wall, okay, of the cooling jacket, and it's kept constant. So the Frank-Kamenetsky approximation, I wanted to hold near T0, okay? So I take the exponential, okay, and I apply the Frank-Kamenetsky approximation here. So it's approximately equal to e to the minus e over RT0, okay, and then e to the theta t minus T0, okay. So it's essentially a constant e theta t minus T0, okay? So theta is equal to e over RT0 squared. That's our first definition, okay? This is, let's consider this as being a capital theta. I'm going to mix things up because I'm going to introduce another theta later on, okay? Actually, I'm going to introduce it now. Okay, that's the Frank-Kamenetsky. Now, let me introduce a few other things. Let me consider another theta. So this is one theta, and this is the other theta, okay? so this is the big one. This is the big one. I'm going to introduce now a non-dimensional temperature. Bear in mind that this big theta has dimension e over RT0. So this is non-dimensional divided by T0, okay? So the overall dimension of this is 1 over Kelvin, right? 1 over temperature. So what I can do is I can introduce a non-dimensional temperature, small theta, taking the big theta here, okay, which is 1 over K, and multiplying it by T minus T0. Okay, that's my non-dimensional temperature. Okay. Good. So let's see. What else can we non-dimensionalize? Well, we can non-dimensionalize time, okay? So I'll introduce a non-dimensional time tau, which will be equal to t times some factor that has the dimensions of 1 over time. Okay? And that would be essentially k e, okay, to the minus e over rt0, for example. So that's my 1 over second, okay? In fact, if I introduce, just for brevity, the constant gamma, okay, then essentially my non-dimensional time is the dimensional time times k0 e to the minus gamma, okay? So I'm introducing all of my sort of non-dimensional quantities, okay? And I can also at this point introduce, as far as the concentration C is concerned, I can also introduce my non-dimensional concentration, which is simply C over C0. Okay? So I'll skip many of those steps because we're not interested in that. I will substitute in the Semenov system and I get something of this sort, okay? So I have an equation for the temperature, the non-dimensional temperature. So you see now that I have a derivative of theta, small theta, okay, by d tau, which is they're both theta and tau non-dimensional, okay, is equal to, I will have a group of quantities here, which are the following. So minus QR C0, big theta, okay, divided by rho CV, okay? And then essentially the non-dimensional concentration times E to the small theta. And then I have another bunch of constants here, essentially HA over rho CV times the volume, and then 1 over K0 e to the minus gamma. Okay, we'll see what those means in a second, times theta. Okay. All of these groups have a physical meaning, okay? And they are all essentially these constants that are left over when we substitute the non-dimensional variables. We can call, in fact, this quantity, for example, P, the whole thing, and this quantity, we can call it U. Okay? On the other hand, the rate of change of concentration becomes dy by d tau equals essentially minus y e to the theta. So that's our Semenov system in, let's say, in non-dimensional variables, okay? Both time, okay, temperature, and concentration, they're all now non-dimensional. Let's see, for example, let's see the quantity P, what it means, okay? In fact, let's take 1 over P, okay? I'll tell you why in a second. So let's rewrite it, okay? This would be essentially rho CV divided by theta divided by minus QRC0, okay? So you can take a look at the units here, and you'll see that they cancel out because there's a density here. Always do this, okay, to make sure that you're doing things right. You can hear me, right?
Sí.
Okay,
Yes.
so we have a density, we have CV, which is a specific energy per unit Kelvin. So it's like joules per kilogram per Kelvin, okay? And then we have essentially, remember, that's 1 over theta, big theta is the units are Kelvin, okay? And down here we have, well, the heat of reaction is joule per mole, okay? And the initial concentration C0 is obviously mole per cubic meter, okay? So it turns out that everything sort of cancels out and you get a joule per cubic meter, kind of, okay? That cancels. So this P, or 1 over P, is non-dimensional. Okay, what does it mean physically? Well, look at this expression here. Well, we have it's a constant volume kind of system. Okay, so rho CV times 1 over theta, which is 1 over theta is essentially a temperature, will tell me essentially this is a rho CV times a temperature, okay? So what it does tell me is that this term is a measure of the thermal energy per unit volume of the system, okay? Per unit volume of the system. Okay, it's how much energy we have stored in the system as a result of its temperature. Okay. On the other hand, down here, well, there is a heat of reaction, so we actually have here heat of reaction per cubic per volume, okay, of system. Okay, now obviously the heat of reaction per cubic per volume of the system is much higher, okay, than the temperature that we can have. For example, the thermal energy that we can have, which I'll remind you, this theta is a measure essentially of the temperature associated to T0, okay? So, which is a low temperature because it's a cooling system. So clearly it's a lot more energy that can be, chemical energy that can be converted into heat than the original heat itself, okay? So this is a very small number, okay? And guess what? I hope you realize that we can assume now 1 over P as a small number, so let's call it epsilon, okay? And that would be, in fact, our famous epsilon that we can extract in the system, okay? That we can sort of conceive for the system, okay? Let's see how we can write the system. If 1 over P is epsilon, we'll have a 1 over epsilon here, okay? So if we call delta U over P, okay? We can rewrite the system quite easily as d theta by d tau is equal to 1 over epsilon y e to the theta minus delta theta, okay? And then here, dy by d tau is simply minus y e to the theta. So we non-dimensionalized the system. We introduced a small number epsilon, and we also end up in a form that is pretty familiar, right? It's very familiar in the sense that it's a singularly perturbed system. Okay, there is a 1 over epsilon here that would make essentially the temperature the fast, and the fast variable, and the concentration the slow variable. On the other hand, remember, I'll just, okay, what is the first assumption that we made at the beginning? Frank Kamenetsky, okay, assumption near T0. Okay, so that means that if this is to hold, if the Frank Kamenetsky holds as an assumption, then we can't really move too far away from T0, right? And so really we cannot use this system. We cannot integrate it, because if we do integrate it, then the system will heat up, okay? It may even explode, and the temperature will be too far from the assumption that it should stay near T0, okay? So you may ask yourself, well, why did this guy do all of that effort in the first place? Why did we write it like this? Well, first of all, because we found a way of non-dimensionalizing. Well, we non-dimensionalized the system in the correct way. We introduced a physically meaningful small number, which is this ratio here, okay? And we wrote this correctly in the singularly perturbed form. If we don't use the Frank Kamenetsky assumption, we can still use this non-dimensionalization, but the expression of the exponent will be a little different, because we're not using the exponential. We're not using the Frank Kamenetsky, okay? But I assure you that we can have, we can put this at good use as well, even though we cannot integrate it. So we can't integrate this, okay? Because T has to be near T0, okay? Now, let me just, for one moment, before we go any further, let me see if I can give some sort of physical meaning to delta also. If you look, these two terms, okay, they have the meaning of Q plus and Q minus. You can always revert back to that meaning, right? The heat added minus the heat subtracted from the cooling system, okay? So delta will have to will have something to do with the cooling, okay? In fact, it's U over P. And essentially, if you write down the actual U over P, you get something like HA over V. Then we have 1 over theta, we're 1 over big theta. And then at the bottom, we have minus QR C0 K0 E to the minus gamma. Okay? So remember, this is the heat, the convective heat coefficient, and this is a measure of temperature. Okay? So in fact, what we have up here is a measure of the heat lost to cooling system, okay, or to the surrounding, if you will, okay? So it's like a measure of Q minus. And under here, we still have the heat of reaction. Now, in this case, you can't really say what delta is if it's larger or smaller than 1, in the sense that it could even be that the heat loss is quite large. It's a dominating factor with respect to the heat of reaction, and you don't have explosions, okay? But that's really the meaning of delta, okay? So let's go back to our system, okay? Even though we cannot integrate it, we can still determine, for example, the conditions of explosions, okay? Of explosion, because remember this, this first term here is Q plus, this term here is Q minus. So this overall terms represents, the heat produced minus, the heat lost through the walls. So, for example, suppose without loss of generality that we have Y, the initial concentration is simply 1, okay? So C equals C0, which it is, okay? If you take this term on the right-hand side, it's essentially e to the theta minus delta theta, okay? So if this is equal to 0, it means that we have a stationary regime, right? So an equilibrium point. Equilibrium point. Remember, this is the same as when we said Q plus is equal to Q minus, okay? In the Frank-Kamenetsky sort of non-dimensional world here, it's this expression here, Q plus minus Q minus, okay? Now, if you remember, the condition of explosion was not just the fact that we could have sort of a stationary point, but it had to be that at this temperature, the slope, the curve of Q plus and of Q minus had to be tangent. Okay, so we also have to introduce this condition that the slope, with respect clearly now to the non-dimensional temperature, okay, of Q plus must also be equal to the slope of Q minus, which now is delta theta, d theta, okay? So this is one condition, okay? So if you remember, I'll just put it in here. The condition was this, remember, Q plus and Q minus. That was our explosion. This was, we called it T star or something. So in this case, the derivative of v to the theta is e to the theta, okay? And this is simply, the derivative of that is simply delta. So this is the second condition. So we have to solve 1 and 2 simultaneously. And what's the solution of 1 and 2? Well, you'll notice that the only way this are satisfied simultaneously is if theta is equal to 1. Okay? So theta is equal to 1, delta is essentially equal to E. Okay? And both are satisfied. What does that mean? What does theta equals 1 means? Okay, well, this is the condition of explosion. Okay, let's see if we can understand it a little bit more if we now go back to dimensional quantities. So let me call this theta equals 1 theta star, okay? The explosion temperature, so theta star is the explosion temperature, equals to 1. Now, remember that theta was defined as capital theta, T star minus T0. Okay, and that would be equal to 1. So we can now very easily see that T star is T0 plus 1 over theta. Okay? So it's T0 plus RT0 over E. Okay, this was squared, so we can put it here. So in fact, the explosion temperature is nothing else but T0 1 plus RT0 over E. So essentially, it's exactly the same result we obtained previously. Okay? Okay, it's identical to the explosion temperature, which we obtained with the assumption, if you remember, that RT0 over E was much smaller than 1. Okay? So if you go back, so I mean, at least we recovered a known result. Okay? But again, that's pretty much the only thing you can do with the Frank-Kamenetsky. You cannot now go back. I mean, if you can't take this system here, okay, this system here, and integrate it or treat it like a singularly perturbed form where we can extract the asymptotic behavior, okay, with reduced slow manifold. You cannot do that because we are stuck in the vicinity of T0. Okay? And in some sense, again, this is what we're doing as well here, okay? By assuming RT over E much less than 1, okay? Now, let's free ourselves of the Frank-Kamenetsky assumption, okay? So how can we say that? Let's forget the Frank-Kamenetsky assumption. Okay, now T can be any value. Okay, not just a value near T0. Okay, so finally we can finally integrate the system or treat it like we want, and we can actually do all our things, all our, let's say, thinking around the singularly perturbed form. Okay, we're almost there because most of the non-dimensionalization that we used before, we're still going to be using it. Okay? The only thing that we cannot do now is the Frank-Kamenetsky assumption. So essentially, this guy here, the exponential, remains in its complex form. Okay? So again, no Frank-Kamenetsky, okay? So how can we write this? Well, we have to substitute now. Now, everything else is valid. Everything else that we've seen remains valid. All of the non-dimensional variables, all of the constants and everything We're just not applying the Franken-Kaminsky, okay? So this exponential, well, if we substitute, for example, the non-dimensional temperature, and remember what gamma was, we have something like this. E over R, and then essentially we have T0 divided by gamma theta plus T0. Okay. Now suppose that I introduce another constant just for simplicity. I've introduced a little bit, maybe too many. We call it beta, 1 over gamma. Okay. This is essentially minus gamma beta theta plus 1. Okay. And if you, so this exponential, sorry, I have to put the exponential here. And finally, if we expand this, essentially, you're left with very simply E to the minus gamma. You can do it by yourselves. I mean, I didn't want to waste too much time here in the algebra. But this, believe me, is the final form of the exponential, okay? In non-dimensional terms, okay? Using the thetas and the betas and the gammas, okay? So that's the only difference. Absolutely the only difference. And therefore, if we are to now essentially rewrite the system, the Semenov system in non-dimensional singularly perturbed form, we have the same sort of thing here. Only difference is that now we have this sort of more complex expression for the exponential. Okay, so I've skipped a few steps here, and the other one is exactly the same. Okay. This should be tau. Okay. This should be tau minus y, and then again here e to the theta 1 plus beta theta. So again, now we can finally give a dynamic meaning to this because we haven't assumed anything. So now theta can be any value. So this finally is effectively, okay, theta is effectively the fast variable. And this y is the slow variable. Okay. For the rest, everything is the same. So we still have all of the above. Okay, epsilon is 1 over p, et cetera, et cetera. Delta is u over p, just as we did before. Okay. Y is c over c0. Fine. So now this is the actual correct singularly perturbed form, non-dimensional form of the Semenov system. Okay. So for this, we can go ahead and we can finally say, okay, if epsilon, okay, shrinks to 0, what we're actually doing is we're shrinking to 0 the fast timescale, the boundary, the temporal boundary layer, and we are exposing the rest. We're exposing the outer solution, so the asymptotic solution, okay? And so let's see what we find out here. Well, if epsilon is 0, the first equation becomes algebraic. And in fact, it becomes our slow manifold. Okay? M0 is the locus of points defined like this. So we put epsilon over here, we let it to 0, and we have essentially y e to the theta 1 plus beta theta minus theta delta, okay? And this is equal to 0, okay? And so we have that that y, okay, is equal to theta divided by e to the theta divided by 1 plus beta theta, okay, times delta, okay? Now, this is in an unusual form because I would have to have essentially the fast variable as a function of the slow variable, but in this case, it's much easier to see, okay? And so this is our slow manifold. So let's go back to, so let's see what kind of form it has. So this theta is the fast variable, and y is the slow variable. And this is my slow manifold. So this is essentially a trajectory leading to essentially this place here, the origin. Why the origin? Because when theta is 0, the temperature goes back to T0 essentially, okay? And we can, for example, start with y equals 1, and the initial temperature theta equals 0, so T equals T0. So the actual solution will be something like this, okay? So we have essentially an increase of temperature in the initial fast transient. So this is the order epsilon kind of transient, okay? We have that the slow variable stays almost constant. So these are the fibers, okay? And then the slow variable, the fast variable will follow the slow variable. So theta will follow y. And they will slowly go back to the origin. So is there an explosion here? Well, in this case, it's not as evident as in the chain branching system. Okay, you can still hear me, right?
Sì, sì.
Yes.
But yes, but look at the role that this delta has. So again, what is delta? It was U over P, and I think I told you before, right? So delta is essentially a measure of the heat lost divided by the heat of reaction. So how do I make my system explode thermally? Well, if I reduce delta, if I make it smaller, okay, than some threshold value, for example, that would mean that the heat lost is much smaller than the heat of reaction. So the system cannot be cooled fast enough, and so it explodes. And so when delta is actually, so suppose that this is a situation where delta is larger than some critical value, okay? If we decrease delta, okay, we are, for example, in a situation like this, okay? So this is like delta, very small, possibly below a critical value. So now the system you see, will go like this. Okay? And then it will slowly go back. So you see that now the explosion is essentially possible. Okay? So the first situation was a situation where essentially we have something like this. Okay? So we have, for example, the Q minus being larger or above most of the Q plus. So we have a stationary point here. Now, clearly, this was a steady state kind of view. So in reality, what happens is that you have the system heating up, but it cannot go beyond this point. And so then, essentially, it will then react and cool, and clearly the reactant will be reduced. So will the heat output until we go back to T0, which is the uniform temperature where we have equilibrium. On the other hand, this other situation here is a situation where, like this, okay, where Q plus is larger than Q minus. So you see that now the explosion is essentially uncontained. Well, it is contained because eventually, okay, this is going to have to stop. Okay? There is a maximum temperature, which clearly is will be near the adiabatic flame temperature. It won't reach the adiabatic flame temperature because clearly now we're cooling, although inefficiently, but we're cooling the system. And so, and then eventually, you know, the reactant will be depleted, and so that's it. So it's finished. The fuel is finished, and the car stops. But clearly, it's still a matter of the shape of the manifold. Okay. Now, back in the day when we were researching this, so this is part of the research. It's very basic. Okay, it's a very basic research. You may think, well, what about delta C? I mean, how can I find the delta C? Actually, in this particular case, you can't really find it directly. So this threshold value, right? I will just tell you a long story in a very short time, but we were thinking about this 15 years ago when we were analyzing we were really concerned in reduction methods and slow manifolds, so we were looking at very basic models like the Semenoff models, and we were wondering, I mean, how do we find, because in the case of the chain branching, it was clear that the alpha, remember, alpha bigger and smaller than 1, you really have a switch of M0. You could see it because the asymptote kind of changed sign. Okay, so the shape of the curve completely changes abruptly, so you have a sort of a bifurcation. In this case, it's a little less evident. And you have to operate some sort of transformation to the system. Because it turns out that if you consider the infinity of the plane, you can actually reduce it to R. So this is R, okay? You can actually do a sort of a transformation and reduce this to essentially a ball of radius 1. So essentially what happens is that this boundary here, okay, is the points at infinity over here. Okay, it's a sort of a very simple transformation, and it turns out that the system can explode when this equilibrium point at infinity, okay, it has one point of equilibrium at which is finite, which is a physical one, but then there is a number of equilibrium points at infinity. This is one of them. If it actually passes this point here, the manifold is like this, okay? And so now essentially we go from a situation like this to a situation where essentially the system can explode. It's quite convoluted. You don't have to know this. This is just for common knowledge. But it's an interesting aspect that we went crazy on trying to understand, and then we had to look at infinity in order to understand what's going on physically. But of course, this is more mathematical than anything. Okay, so you don't have to know this. The bottom line is that if we have a heat loss which is small, we're not cooling the system far enough, so we are on this manifold here, okay, and therefore the system can actually explode. Okay. Let me just tell you the very last thing, which is this. You can also take the equation of the manifold and vary beta, okay, which is the activation energy, essentially. And you can do the same kind of reasoning, okay? So if beta is larger than a certain threshold, this means that this is low activation energy, and you have M0, which kind of limits the trajectory. But if beta goes below a certain activation energy, so remember that beta was 1 over gamma, so it's essentially 1 over the activation energy, the non-dimensionalized activation energy. So if we have high activation energy, then you see that the system can actually explode in a sort of a limitless way. So the trajectory is not bound, okay, by the manifold. It's not constrained by the manifold, and the temperature can increase. Now, clearly, this is still the temperature, and this is still Y. And with this, essentially, we have completed our analysis of the so-called toy models, this chain branching and the Semenov system, and all of the sort of the use of these fancy, old-fashioned kind of mathematical techniques, such as perturbative analysis and singular perturbation theory. And I hope you realize that we have been able to understand a lot more with paper and pencil than just maybe taking the equations, the ordinary differential equations, and integrating them numerically, although that you can actually do, okay? You can integrate those equations numerically. And if I have time, I will show you how to do them with Cantera, okay? So let's see very briefly, okay? Now, we've seen the chain branching. We've seen the Semenov system. They're very simple for the overly simplified systems, okay? The first one is at constant temperature, okay? Considering 3 steps, an initiation, a branching, and a termination step. That's the chain branching. And then on the other side, you have Semenov, which is a thermal explosion. So we don't care about the mechanism where we have no intermediate species. We just have a one-step reaction, but we retain, okay, the exponential function dependence, the functional dependence on temperature. Now let's put everything together. Real systems, actual systems, okay? What are real systems? Well, these are systems where we actually simulate, okay, the combustion of an actual mixture, a flammable mixture, explosive mixture of, say, an hydrocarbon like methane and an oxidizer like air in a container, okay? Now, there are 2 ways of doing this. Okay, we can keep the volume constant. Now, clearly, if we keep the volume constant, the pressure will increase. Okay, so here we have essentially a set of fuel and oxidizer with a certain initial composition, okay? And we increase the temperature, or we let it evolve naturally, and this will explode, okay? We can also have external walls, T with some sort of Q minus being subtracted, okay? On the other hand, let's consider it like a piston, for example. We can have, so this is a V equals constant system. We can also have a system where we have a variable volume, okay, but the pressure is kept constant. So how do we keep the pressure constant? We expand the system, okay? So the system now expands with this piston, okay? So the pressure is constant. Now the volume now actually increases, okay? And this is, again, my flammable mixture. So the question that I'm asking is, how do we write down the actual equations, okay, the ordinary differential equations for these spatially homogeneous systems? Remember, there is no space. This is all homogeneous. The ordinary differential equations, for example, for all the species, the mass fractions, for example, and the temperature, for a real system. So a system that is composed of, say, a number of species. So the initial, clearly reactants, but also the intermediate species and the products, up to any number, even 500. Okay? So we are really carrying out an extremely detailed analysis of what happens during the explosion of the system. And clearly we need the chemical kinetic mechanism composed of thousands of reactions, or maybe a little bit less, that I showed you some time back. I'm going to need also, of course, some information about the species, okay? But how do we actually write it in dimensional form, okay? Or so, oh, we have some time, right? Yes. So consider now first the constant volume system, this first one here, okay? Are you still there?
Sì, sì, sì.
So, how do we write down an equation for the temperature of this thing? Of course, the temperature will increase, right? And eventually, if we don't lose any heat to the surrounding, it's going to reach the adiabatic flame temperature, okay? At constant volume, which is slightly different, slightly higher than that at constant pressure. Why? Well, because the constant pressure system will be making work, right? Because of the volume changes, and so it loses a little bit of energy for that work done towards the surrounding, right? That's pretty clear. So how do we write down an equation for the temperature? Well, we have to somehow implement some conservation of energy, right? So how do we write down the conservation of energy? Well, the same way we always write it. So the change in internal energy of the system is equal to the heat exchanged with the surroundings and the work exchanged with the surroundings. Okay? Now, at constant volume, obviously, dV is equal to 0, so du is simply the heat exchanged, which could be 0, by the way. So if the heat exchange is 0, we have an adiabatic constant volume system. Okay, but let's keep it general. We're going to be dealing with, generally speaking, we're going to be dealing with specific quantities, okay? So remember that specific, that's supposed to be a small u. So that's per unit mass, okay? And how do we write this per unit mass? I don't know, I have no idea. So let's put like a little hat. So this is specific quantities. Per unit mass. Okay. I hope you remember some thermodynamics or thermostatics. U, okay, the extensive quantity U, okay, was equal to number of moles times the partial molar internal energy, remember? But the partial molar internal energy was equal to this, to the molar, okay? Internal energy, okay? Maybe let's put a little thing here to differentiate it from that per unit mass, okay? And so, if now we want to introduce the specific value of U, the specific internal energy, well, we take the number of moles, we multiply by the molecular weight of I, okay? And then this would be now my specific per unit mass, okay? And in fact, that number of moles, this number of moles, we can write it as a mass of I, of the ith component, divided by Wi, U. So essentially, in mass form, it would be MiUi. Okay? So we're summing on all the species, right? And so the specific internal energy is essentially the extensive quantity divided by the mass, okay, which is nothing else but the summation of Mi over M times Ui. So this would be U, and Mi over M is the mass fraction. A very long story to say that U is essentially the sum of the mass fractions times the specific internal energy of the system is the sum of the mass fraction of all the components of the system times the species specific, the pure species specific internal energy. Okay. So we can now write finally du, right? Because now du, okay, will be equal to, well, ui dyi. I'm just differentiating that expression, plus the summation of dui times y. Yes? And in fact, dui is also equal to C, the specific volume, the specific heated constant volume of species I times dt. Okay. What about ui? How do we express this guy here? Well, remember that in extensive terms, the enthalpy is U plus PV. We also know that the partial pressure, this is the equation of state, the partial pressure PI times V is equal to R, the number of moles, times T, okay? And that the mass is the number of moles times the molecular weight. And so essentially, PIV can be written as R times, divided by the molecular weight times the mass times T, okay? Which is well, we can write this as the gas constant of the gas I, okay, times the mass times T, okay? So this would be essentially HI UI plus PIV for the species I, divide by the mass, okay, of species I. We finally have the specific enthalpy, okay? And this would be equal to what? The specific internal energy, and then this guy here, PIV over mass, okay? So finally, the specific enthalpy is equal to UI plus, well, this quantity here, PIV over M is equal to this over M, so it's R by T. Okay? And so let's go back to our du. Okay, du can be written as the sum, okay, of now ui's can now be written as the enthalpy of the species I minus RIT dy. And then, well, du is simply CV I dt. Okay, I'm writing this term here times y. Okay. And this is equal to dq. So all we have to do now is, well, CVI, so this term will be dt, CVIY, right? If you remember, this is the mixture averaged, sorry, this is the mixture averaged CV. So the specific heat at constant volume of the mixture. We can define it with a little bar ups, or sometimes you can also write down CV mix. Okay, just to say, but it's the sum. It's the sum of the CV times the individual mass fractions. Okay. And that's it, it's done, because now we divide by dt, the time, okay, and we have essentially the sum of hi minus rit, then we have dy by dt times, plus the mixture average CV times dt by dt is equal to delta Q, okay? So we have essentially an equation, dq by dt, sorry, which we can call it, I don't know if you want, we can call it Q dot, okay? Well, we have an ordinary differential equation for the temperature. What about this term here? But we know exactly what this term here is, right? Well, first of all, remember that the molar concentration is rho divided by Wi times the mass fraction, okay? And we also know that the rate of change of molar concentration is omega I, okay? So it's essentially, if you have NR reactions, okay, if we sum in all the reactions, is for each reaction is the difference in stoichiometric coefficient, okay, times the reaction rate of each reaction. Okay, this K stands for a reaction. So you can really sum on this could be 1,000, okay, and more reactions. Okay? It doesn't really matter. You can very easily compute it in an algorithm automatically. Okay, and of course you will have 1,000 ODEs. Okay, quite complicated. And of course, well, omega k, as we know, is omega k forward minus omega k backwards, okay, et cetera, et cetera. So this would be k forward times the product of all the molar concentrations, okay, minus, you remember, right? I don't have to rewrite it every time. So, the final system, okay, is the following. dt by dt is equal to -1 over CV of the mixture, the sum of this enthalpies minus RIT, and then this would be dyi by dt, okay? And then this source term, which is 1 over CV dq by dt. And then we have a series of equations for each species, okay, which are simply the molar molecular weight divided by rho divided by omega dot I. That's it. This can be implemented this can be implemented in our system. Okay. Of course, this could be in the form Q minus, right? So this could be minus H A T minus T0 or something, okay? Over V probably. You have to check the dimensions here. The constant pressure is the same. Now, if you give me 2 seconds, okay? So I would have done this if, can you have 2 seconds to spare? Well, I can show you how these can be solved numerically in an extremely efficient way. So what I'm going to try and do, if I can do it today, maybe I can try and do it tomorrow. But tomorrow you have a special lesson, and I suggested you all come because we want to show you now that we've done a lot of theory, a lot of practice. Okay, well, we're going to show you essentially what the latest in numerical combustion really has to say. Okay, so putting computers, and by computers we mean supercomputers, to use for combustion scientists. Okay, let me see if I'm not too sure if I can make it now. Can you still see?
Si vede la lavagna?
Sì, la lavagna. Adesso aspettate un attimo che... purtroppo quando le cose vanno male, ragazzi, ecco. I mean, for those of you who need to go, you can leave right now. It doesn't really matter. But if you're interested, I'll just take maybe 2 minutes. I'm starting the Python. It was all set up before the system crashed, so it takes a while for this. If you're familiar with Python, you know what I'm talking about, right? Okay. Let me stop sharing. Okay. Well, I'm not too sure I can do it now because at least I can show you. So codes local, let's see. Oh no, I don't have to do that. Okay. So can you see something now? I'm sharing my screen. Oh God.
Yes, Professor.
So if you can see this, this is, can you see the screen?
Sì, si vede, si vede.
Sì,
Okay.
sì.
So I don't know if you're familiar with Python. So what I'm doing here, I am importing this Cantera, okay? Now, Cantera is essentially a big library written in C++ that will do all of the thermochemical things for you. It will calculate, it will import a big, huge, if you will, mechanism of reactions. It will calculate all the reaction rates, everything for you. So you don't have to do anything too complicated. All you have to do here is specify, go back to your notes now, right, and specify the system of ordinary differential equations. So you see that we have a dt by dt for the temperature, which is rather similar to what we wrote, okay? And then dy by dt for all the temperature, for all, sorry, the species. So this subroutine here will essentially, or class, in fact, return the right-hand side of the temperature and all the species. Then you essentially specify the mechanism. In this case, it's this GRI, which is a very known, very famous mechanism. About 54 species and 300 plus reactions for methane. In fact, here we're reacting only hydrogen and oxygen, but you can actually react anything. There is an initial temperature of 1,000 Kelvin, okay? And you integrate this, the ODE, okay? And this is what essentially you get, okay? So you have this line here on the left is the temperature, and you can monitor now all of the species. So you have, for example, here a reactant, okay, which decreases. And you can see here you have an intermediate, which is OH, okay? This is exactly, so here it is, okay, the ignition time, then you have the intermediates, okay? And finally, the reaction that takes place. So very, very similar to what we've done, what we've seen in the chain branching, although this is both. This is chain plus, okay, thermal explosion, because clearly look at the temperature here. It goes from 1,000 to 2,500, okay, degrees. Okay, so that's more or less a very basic thing. Okay? It's a zero-dimensional thing. Then, of course, when you want to solve for flames, it's going to be even more complicated. But you can download these at cantera.org. and run them yourself. Okay, and you can change the temperature here. You can change this is the molar composition. Okay, you can see how that here you have air, so you also have nitrogen, but you can change this to whatever you want. Okay, as long as it's not more complex than methane, so CH4, and you can solve this. Okay, so I hope that was clear and it was sort of clearly seen. So if you have questions, if there's someone left, because maybe, okay, there are some of you left. Okay, so tomorrow please do come, because Pasquale actually is going to introduce, well, I'm going to be there. So we're going to talk about the latest in terms of turbulent combustion simulations, okay, in rockets and combustion chambers and things like that, okay? And you'll see how far more sort of the distance between what this theory and that application is really not that huge, okay? So the hard bit is what we're doing in the course, okay? Anyway. So if you want to have a go at these things, it's fun. It's all free, okay? It's all open source, Cantera, so you can download it on your computer. It's all for free. And so you'll put the theory into practice in just a blink of an eye. Very good. Okay, if there are no questions, then we can close it here.
Arrivederci.
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 Arrivederci.